Okay, so here we have exercise 12.5, and we are given that our inertia 1, 2 axes are equals to 90 kilograms per meter squared, meter squared, and I3 is equals to 140 kilograms meter squared. Now our initial angular velocity vector, so times 0, is equals to 0.126040 u1 minus 0.072769 u2 and plus 0.684703 u3. Okay, and we're asked to find, are those admissible or not? Well, looking at the first one, actually, let me take a picture of all of them so you can see it on my screen. Nope. Nope. I don't understand what's up. Let me try again. Anyhow, meanwhile, the idea behind it is that we need to calculate if there's conservation of angular momentum. Okay, I don't understand why it's not wanting to do it, and I want to copy it and paste on my. Okay, whatever. Anyhow, so we have our bulk values. The thing that I want to point out is that our omega 3 at times 1 is equals to our omega 3 at 0. So we can kind of ignore it, as in, if we want to find our angular momentum, h, then we need to do I1, let's say I omega. Now vector is a matrix, okay? Right, and then we want to find if the angular momentum magnitude is conserved. Now, if we want to find that, one thing we can look at is how does the velocity change itself? So if you look at the first one, we only have a change in the sign of the U2 component, meaning that this thing here will be the same apart from the fact that H2 will be equals to a negative H2. 2 times 1 will be negative 2 times 0. But the magnitude of the two will be the same. The absolute value, but the magnitude, that's what we're going to use. Therefore, it is viable because the angular momentum is conserved. For the second one instead, we see that our omega 3 at 1 at times 1 is different than our omega 3 at times 0. And it has gone down. The other two, however, have remained the same. So the h at times 1 is lower, I guess I'm going to do this, than h at times 0. Because one of the components has gone down, meaning that our h3 at times 1 is lower than our h3 at times 0. Therefore, the angular momentum is not conserved, and therefore there must be some other force. So this is not a viable, a feasible, that's how you want to call it, a feasible velocity if there's not external torque. Now for C instead, we see that the omega 3 at times 1 is the same as omega 3 at times 0. However, omega 2 at times 1 is higher than our omega 2 at times 0, and our omega 1 at times 1 is less than omega 2 at times 0. In this case, then we actually need to plug in and find our H matrix by doing H omega W, and then finding the absolute value of H, which turns out to be the same as the absolute value H 8 times 0. Therefore, it's a feasible option. Then D, by looking at it, we can see that our omega 3 at times 1 is the same as omega 3 at times 0. Then our omega 1 at times 1 is less than our omega 1 at times 0. And our omega 2 at time 1 is also less than omega 1 at time, omega 2 at time 0. meaning that we have a definite decrease. I mean, one of the two has to make up for the other, but there's no such makeup. So the h1, the magnitude of h1 is going to be less than the h0, and therefore it's not feasible. We need to slow down somehow, but without external torque, we cannot slow down.